Thank you very much. Nice to speak here. Thank the organizer for allowing me to do this. So I want to tell a story which is not quite finished. So you saw that I changed pictures at the last moment, and not all of them okay, the date is correct. So the subject, we will consider topological invariants of tangles. Tangles are things like that, and I think that in this audience I shouldn't explain what are tangles. Definitely the main object would be links, but there are a few reasons why it's better to consider tangles. Yeah, first of all, the tangle should be oriented, because it will be Alexander polynomial, which depends on orientation. And it should be colored with elements of a free abelian group. So it should be like that. So what are the reasons why tangles instead of links? First of all, links are served. Of course, as usual, you can convert a link into tangle just to make it a fake tangle. But also, it's better to even disclose it. Why it's better to disclose? For the categorification thing that I want to speak about, it doesn't matter. But the Alexander polynomial, if it is done in this way, when the link is closed, is identically 0. 0 can be categorified by non-zero. Just 0 Euler characteristic may happen. And another reason, tangles gives a little bit more. They give rise to a functor, to the category of modules over the polynomials, over the elements of this ring. So it will look like that. So we have a tangle. So you put on the bottom the tensor product of z squared, as much copies as you have on the bottom, and similarly on top, and this would give you a linear map. So for F is a free abelian group, which is fixed.
Is it z squared or z of f squared?
Z of f.
Z of f squared.
Yeah, probably z of f is also, well, both will be served, I suppose. So it depends if you color with this.
If you already fix the colors, then it's.
Yeah, if you already fix the colors, then it is z squared, which is. Right. So I'm going to categorify an old construction which assigns to an oriented colored tangle an Alexander polynomial. And this old construction is a version of Reshetikhin-Turaev construction. And originally it was done by Reshetikhin, Rozansky, and Solor, if I didn't forget anyone. I don't remember, Lou, by the way, was your paper with Solor before Rozansky, Solor, or after? There is a common co-author, and definitely I learned from both of them about GL11.
We understood at some point, Solor and I, that you could take the Burrell representation and let it act on Grossman algebra and get a solution to the Yang-Baxter equation. Now,
but it was
whether that's due to us at first or someone else.
I think it was before Rozansky, Solor. I think your preprint came before.
I'm sorry?
Your preprint came before Rozansky.
But maybe then it was without GL11.
I'm sorry.
No.
It was without GL11. It was with.
Well, we were using
No,
GL.
no, there was
you-
no. Yeah,
okay, so I have to change.
Kazantzky summer maybe was more about three-manifold invariants.
No, there were no manifold invariants. So I have to say also about other approaches to the same subject, and there is a note for and grid homology. So another categorification of multivariable Alexander polynomial. It was done in 2002, 2003, and it was based on completely different ideas, and therefore it has its advantages and disadvantages. Advantages is that it was already a long time around, and it was used in many ways. There were many results built on this categorification. And disadvantages, it is very inconvenient for computer calculation. So it's not that bad for calculations, because in the very first paper about that, they already calculated the homology for nodes up to 9 intersection. So it was not that difficult. But on the other hand, it should be each time looked at this picture and realizing. It was not combinatorial in the following precise sense. For nodes with homeomorphic diagrams, could happen that the construction provided different complexes, differentials depended on that. So what I am trying to do, yes, and there is a combinatorial version of node-Floer homology, but then it is with huge complex. So again, calculation is not easy.
It was over Z2 or over field?
Over Z. Well, it is.
Calculation was up to 8 crossings over Z, really?
Does it matter?
I don't remember any Tolja.
I don't remember either, but does it matter? Anyway, it is categorification. It is a categorification. It is not, it may be slightly less informative, but at least it is upgrade coming just in time. I am discussing node-Floer homology. So at least what I'm going to tell you is completely different, and in a sense it is more elementary. Everything will be in pictures and not of in unusual setup of grid diagrams. I hope that at least it is simpler. Now, we have to present the Alexander polynomial of a tangle as a state sum. And the tangle is presented by a diagram. Assume that the diagram is generic as usual, so usual diagram, and the maximum and minimum on this diagram are generic. So it should look like that. And it is colored and oriented. Okay? Now, what is the state of a diagram? It consists of two parts. First, a distinguished set of crossing points. I'm not sure that I want to preserve this strange name, but I just wanted to say that there are some terms there. Chance, is something which is changing the direction of tram on a railroad, or blood in blood vessels. But anyway, just a set of crossings is selected, and at each of these selected crossings, we have to choose a sign, plus or minus. So this is the thing. But it shouldn't be arbitrary. There is some special condition that should be satisfied, which decreases the number of states. So what is the condition? The only restriction is that the chance should alternate between over and under crossing as we travel along the street of the tangle. So if you think about this tangle as about virtual with only chance crossings real and the rest of them virtual, then this condition means that this is alternating. The diagram is alternating. If you forget about everything but this selected
If every crossing is a shunt, then the diagram must be alternating.
Yes, but on the other hand, if none of them is a shunt, it's also alternating. The condition is satisfied. If one crossing is shunt and the others are not, it's also satisfied. But when you have two crossings and they are shunts, it may happen that, well, this condition is not satisfied and we should throw this away. Say for trefoil knot, standard alternating knot, we have just all crossings forming a shunt. Then one point, each one crossing forms a shunt and empty. No two give a shunt.
And in this picture, how many shunts?
I will show now examples. So this is what is surrounded is a shunt. Here it is so. But again, this is a structure. This is a state. We have to sum up some expressions over these states. I have to put there also at each of these circles plus or minus, and this should be like that.
But the crossing types are the ones that came from the original tangle?
Yeah, the crossing come from the original tangle.
So you select some subset?
Yes, yes. So you see, this is up, then down, right?
Yeah.
Now along a blue curve does not count up, down, and that's it.
And if I change the orientation of the third thing, it will also become a shunt, or it is my choice? Or what?
If you change orientation, it would still be a shunt, but we do not change orientation because it is in the structure.
I mean, if I change this crossing, so then there will be three shunts, or
if you change this crossing, at least this one will be
I
a
can
shunt.
call it a shunt.
Yes,
but
you
should I?
can call it a shunt.
I think it's up to you, I guess. I think
It's
it's
up
up to
to
you.
So I can treat it as I like. Yeah?
Okay, and in the next example, you may see that we have another state, which is made just of this single, and then it's a wrong collection.
So the diagram has 5 possible states.
Hmm?
This diagram has 5 possible states.
This diagram
And the
has
diagram, this tangle has 5 possible states.
No one state,
Uh,
no shunts at all.
No
Yeah?
shunts when one shunt.
At the blue crossing.
No, any
So-
crossing can be shunt, right?
First of all, the very first picture gives you already 4 states, because you have to attach to each crossing plus or minus.
Oh.
Then the second one gives 2. Then there is nothing. Then you have 1, and that's
You
it.
have 2 more crossings for 4 more states and the empty.
Yeah.
And the empty.
Yes, 2 more crossings for, yeah. Okay. And
But it's just a definition, so we shouldn't understand the motivation.
I will explain now why. It is. I discovered this definition recently, and I was forced to. So it's not that I had to invent something. I just had to observe.
Once more, so the sign of shunt has no relation to the sign of the crossing.
No,
Just arbitrary.
just arbitrary. Then for each state we have some extra decoration. First of all, the shunts subdivide strings into parts, and they are classified into bosonic and fermionic. And this is closely related to GL11, which will be here in a few minutes. So what is the definition of bosonic and fermionic? Bosonic part starts at a borderline. Oh, say may happen like this. Oh no, this is not bosonic. No, this is bosonic. So it starts at the borderline and finishes at a crossing, but over crossing. And then after that it follows fermionic, and then again bosonic. Bosonic starts on undercrossing or boundary and finishes on overcrossings or boundary.
So you ignore the crossings that aren't in the shunt?
Yes, which are not shunts.
Which are actually.
And you also ignore the sign assigned to the shunt.
And I don't need sign for at this point.
For this example, on the left, the blue strand will be bosonic fermionic, bosonic fermionic. For the picture on the left.
So these notations will change, but now I put bosonic into dotted curve.
But why is
So in the first one.
You ignore the crossing. That was
why is the third? Sorry.
Which one?
This picture is impossible.
Yeah,
This picture is impossible because, well,
yeah, the picture on the left.
okay, let me show all the pictures here. What is wrong?
But I don't understand the bosonic fermionic assignments in the leftmost picture.
In the leftmost,
Yeah, for the blue line.
we first have, say, this blue curve.
Yeah.
It starts on the boundary and comes to the overcrossing,
Yeah,
where
so
it
that's
should stop.
bosonic.
And this is bosonic.
Yeah.
Then it follows fermionic, and then again bosonic. It starts in undercrossing and goes to the boundary. With green also it is.
But why is the third part bosonic? Okay, because it starts.
the crossing's not a shunt.
They alternate.
Oh, because it's not a shunt. It's not a shunt.
I could write also everything about fermionic, but it would
So
be.
they always alternate. So bosonic
Yeah,
means
they
alternate.
always
for
alternate.
any-
And is it a rule that if it started as bosonic, it ends as bosonic?
Yes.
So that's obligatory.
Oh no, and at bosonic. No, it may happen that it just frames.
So you can convert it.
Yeah, it can be whatever. But they finished there and start there somehow. So it's
But
both.
it's not that you can take a trace obligatory. It's not always possible. Yeah.
No, and let me explain why this rule comes.
But I don't understand. So it is unique.
This rule is.
It is unique when you have diagram you know already, or this is part of the criteria only?
No, the state consists of assignment of these shunts and signs.
And
Signs
they
are not
decide.
relevant, but at least for this distribution between bosonic and fermionic. But as soon as you fixed the crossings, shunts, you know which is which. And the origin of this is in R matrix. Because shunts are where R matrices have binomial.
But you didn't explain in the middle picture why green is fermionic. Yeah, it could be bosonic.
In the middle,
Yeah, in the middle. Green could be both bosonic or fermionic. It's arbitrary.
oh, yeah.
What are the shunts for the middle?
There are
You
no
are
shunts in
right.
green, right?
There is no chance there, and it could be any. Yeah, you are right. So my formulation was sort of incomplete. If there is no
Actually, it was
chance.
complete because you said that at the bottom it should be bosonic. So,
What
No,
are
but
the
it is
shunts-
fermionic
shunts
here.
for the
yeah,
middle?
but the
Green
picture
is-
differs from the explanation.
What are the shunts for middle picture?
In
Just
the
one
middle
shunt?
picture, the shunt is
Just
only
one
this
to the left.
one.
Yeah.
We should remember this from the previous.
So the whole green thing should be dotted in the middle. Is that right? Because you
die.
said at the bottom it has to be bosonic.
It's present. It's present, but it is present, so it cannot die. But for our reasons, but it cannot be divided. It is not divided into bosonic and fermionic. Either it is the whole fermionic as it is shown now, or it is the whole bosonic.
It can be either.
Yes, and
So you have to state to different states.
yeah, yeah. So there is a little bit more states.
You have two And each one is a state?
Both.
So each one is a state?
Each one is the state. I'm sorry, I had to add that distribution into bosonic and fermionic should be included, at least in this situation. This is a special situation. Usually it does not happen, but when you have no...
When you have a strand which doesn't offer any chance, it can be either bosonic or fermionic.
Yeah, so the same happens if there is no chance at all. Yeah.
So am I to understand that on the left, could I have started out as fermionic, the blue coming out of the bottom? Could it have been fermionic and then become bosonic?
Well, here,
yeah.
No, you have no chance. Because here it is overcrossing. At overcrossing, the bosonic part should finish.
So then in the middle one, should you have written it as dotted or?
It may be either dotted or not.
Why?
But because there is no chance.
It's not going through chance.
Not going through chance.
But why is in the middle green can be fermionic? I don't understand. Oh, sorry. Yeah. Why is?
It does not. It wouldn't violate any restriction.
Because you don't have any restrictions on the fermionic parts.
Well, on the fermionic part, it should start either at the border or at overcrossing in the shunts. In the shunt. Here we have a border where it starts. It may start.
So this is the bosonic part start with the border. Or
I had just to add this description for fermionic either, just to cover this unhappy situation when there is a string on which there is no shunt.
And if you have a close component that has no shunts.
If there is no chance, it can be colored in either way. Yeah, that's right.
We probably missed what you said. You said that you can read what is bosonic and what is fermionic from the R matrix, yeah?
Yes.
You said this, but we didn't pay attention to it.
Yes, so our matrix looks as follows. First of all, what is this our matrix? It is coming from GL11. GL11, so we have representations, two-dimensional representations, which is super dimension 1, 1. So one bosonic, one fermionic. What is happening here? We have already color with representation, which is twisted by an element of free abelian group. But in the heart of it,
if I look at it as a matrix, is it different from SL2 in this case?
It is not much different. It is.
So that's just the same matrix, only you ascribe some additional labels saying what is.
No. There is an element which is of different sign, but it is on diagonal. When you have two fermions, it should be negative, and the weight is different. But the important place where the shunts are is when you come to this crossing with a bosonic and fermionic vector. And then it may happen that they just penetrate through each other. And then this is not a shunt.
And you need GL11 to describe Alexander.
Yes. Well, instead I can use SL2 with a square root of -1 as, but this is just a modification of the same construction. And here I select representations secretly. I have to write down representations probably. And I will do this in such a way that the framing doesn't matter. There is a version with framing turned on, but I want to stay just with, for simplicity, with standard Alexander polynomial. Okay, this is not done. Now, Boltzmann weights. So when we have a state, we should distribute, we should attach to critical points to maximum and minimum, and crossing points, monomials, out of which the whole polynomial will be built as follows. For each state, you take the product of these monomials and then sum up over all states. At crossing, at maxima and minima, the distribution is like that. Here, dotted are bosonic, solid are fermionic. I don't know what notation is better, how physicists do it. Do you attach any color to bosonic or fermionic? I will use some. Yeah. Okay. Well. And here, what is happening at crossings?
Your multivariable.
Yeah, this is multivariable. So U and V are colors of the left and the right string on the bottom.
What was red and blue? Sorry, what is red and blue?
Red is bosonic, blue is fermionic. Now, I'm afraid that I didn't reorient everything because I decided that I wouldn't reorient fermionic. It was originally reoriented for some strange reasons. So now I get rid of this, and here in this picture, all the arrows should be directed upwards. So for other orientations, there are slightly different ways, not much different. Besides, no, it's everything is.
But this is some simplest representation.
Yeah,
So you
absolutely.
can take other representations.
There are other representations, but
and still there will be this red and blue division, yeah.
Because if it is of dimension 1, 1, then you have.
But each red can carry some representation, and each blue can carry some representation.
So look, they carry not only representation; they carry also element of canonical basis. Here, basis is canonical because it is just made of bosonic and fermionic. Each part is one-dimensional.
So are these rules for shams or for arbitrary crossings?
For the rule for chance is because when you have a switching of bosonic and fermionic part, at the overcrossing, you have orientations. Oh, no. Not orientations, but bosonic part comes to it. So this is a wrong picture. Here I didn't reorient it. It should be like, I didn't reorient it.
The blue arrow should be pointing up, is that right?
Everything here should be pointed up.
Okay.
So,
So this is a form of a sham crossings only?
so for bosonic, you have to come to here. Wait. Yes. And this is fermionic. And here, so the rule is like that. In a matrix, the other elements are zero. The elements where everything is all the way around comes with zero coefficient. So in this matrix, the non-zero coefficients stay like this. So this diagonal terms, when you have just bosonic, and fermionic, are non-trivial. And here is the main difference from the Jones polynomial. Here there should be negative sum. And here is non-trivial, while there it is zero. Okay? And in this non-trivial place, we have really two terms, two monomials. with opposite signs. So they are divided between two states. So we introduce extra structure at this shunt point. To have
those shunt points, so our shunt points, you can a single label.
Yes, yes. So I have to assign here plus, and then it will come with u squared, or minus, and then it will come with negative u to minus 2.
And if the crossing is not shunt, it doesn't contribute to a particular term.
No, it does contribute, and these are the terms which
So
are.
all crossings contribute.
Yes.
Contribute. I think that shunts are the only ones on the right, in the right column.
Yeah.
So any shunt appears on the right column only, and non-shunt appear in the other 4 columns.
Yeah.
But in principle, I could just put this 4x4 matrix and forget about all shunts and everything. Yeah,
Right. But the idea is that when you evaluate when you multiply all these matrices, you get a matrix connecting generator here and generator there. Okay? So with each distribution of generators up and down, you have a number, the matrix element. The matrix element can be obtained by this graphic procedure, as usual. Product of all the terms which appear on this picture. And we then respect this canonical basis to such extent that we consider this distribution of this state as a generator for the chain group.
But if it was not a tangle but a knot, the basis wouldn't matter. So it would be invariant.
It would be invariant, deadly invariant, equal to 0. When you make the sum, no. Of course, you can do this. You can do everything, but this is a theorem that in the case of GL11, when you consider the state sum for closed, you have 0, and to get Alexander polynomial, you need to cut one of the strings to put the endpoints up and down and consider the corresponding 1-1 tangle. It is just multiplication by a constant.
So not a trace, but a matrix element of this whole thing.
Yeah. It is called somehow trace. What is modified trace or something? There is, and it doesn't matter which string you cut, and you have to divide by after that by an invariant of the unknot. So to compensate to the choice of string. But if we go ahead with homology, it doesn't matter. We can do in either cases, and then
in principle, what it was badly needed that you have this matrix which is off diagonal at a single place. Yeah.
Yeah, but
if we go to higher representations where it is very much non-diagonal, so
yes, then I believe that we would need topology, not homology. You know what is homology?
what is the word?
Topology.
Topology.
And this is for generalization of homology. When you have nilpotent operator, but the degree of nilpotence is arbitrary, is fixed and higher than 2. Because then you have many things to put differentially.
Could you show the previous slide again for just a sec?
Yeah, here it is.
Yeah, I guess I'm wondering about the symmetries of these assignments. So, you can see that if you reverse a crossing, you send the labels to their inverses, I believe?
Yes, so this row differ from that by changing the sign of the crossing. That's right. And in this way, then you just take the inverse. So it can be described simpler, but then several statements. And then in a straight crossing, which is not a shunt, you take the variable to power which depends on the other string. if the other string is, consider the positive crossing. If the other string is bosonic, then you put +1. If the other string is fermionic, you put -1. It's again just a description of this matrix. It's not something that.
What does U and V refer to labels of the components?
So this is U string and this is V. U string which starts in the bottom left corner and goes upwards and to the right.
And
so
what
it's,
about if you swap bosons and fermions? It seems to have a symmetry with respect to that as well.
not exactly. It is supersymmetry, you know.
Okay, the supersymmetry.
For example, here we have sign -1, which is because we have here two fermions, and we switch them. And when you switch fermions, it's skew-symmetric. The sign should
So it behaves
jump
like
out. Okay?
And one stupid question. So you alternatively can get Alexander by analytical continuation in N, yeah, from Comte. If you take Comte polynomial and put n equal to 0, you get Alexander. Yeah?
It's a specialization of the variable Home-Flippity polynomial.
Home-Flippity.
Yeah.
Yeah. So it's not.
So you can alternatively get Alexander in this way. Yeah.
Yes.
Why it is the same construction? Is it obvious that what you get from this GL11 is the same as there? Or is it just a coincidence?
Calculations.
You can check really the definition, scaling relation. But other SLN or GLN can be treated sort of uniformly. They were treated uniformly, but this case was always
I understand,
somehow outside.
But a posteriori, after you know this, is there any clear reason why as GL0 is GL11?
No, I don't know. I don't know. There are also versions with not GL11, but GLPQ, whatever. And it is just more complicated. I wanted to stay on the simple ground, not too complicated, because Alexander polynomial is a nice thing. It is known to be related to Seiberg-Witten. As for other GLPQ, who knows to what they will be related and maybe not. So let us just stay with something simple. Okay. Then let us consider what's happening with the state sum. Consider invariance with respect to the first Reidemeister move. I didn't put here all the pictures. There are more pictures. But anyway, if we fix coloring at the endpoints of this fragment, we have to consider just those pictures. So if we start with a bosonic string like this, going up, we can have a shunt in this point, or no shunt at all. And for each case, we can find contribution of the corresponding part. And you see that these two contributions eat each other, and this one is the same as there. So what should happen?
I'm not sure that I understand the difference between the two pictures, second and the third.
Well, the difference is that here should be plus sign and here should be negative sign. I didn't put it. They are both shunts, but with different signs.
So you pick up this different
So
squared and minus.
yeah, so I fix the state, and it is not shown here. The picture is old, when there was another way to mark signs. But anyway, it is clear that this is preserved, and it should be, and it is well known that it is preserved. It is from these old times, so it is just a state sum. Here is a similar picture for other colorings. I do not give all of them, because what is what should be other pictures? It can be also on the other side. This is right, positive and negative kinks. There are also left, and we can turn it upside down. But basically, that's it. The others can be obtained from those. And it is clear how the differential should behave here. It should map this state to that. Then, since the image of this state is, and all the extension of this state, keeping the rest of the state, just changing this point from non-shunt to shunt, if it is possible, due to distribution of other shunts, we have to have a differential. Then, since the image is non-trivial, this state dies. And since this state is the border, the boundary, then this also dies. So to have homology, we have to have this kind of differential. And similarly here, we have only one thing.
So you already said that the basis of your homology, of your chain complex is
States.
Yeah.
Yes, that's fixed. Now, what happens in the case of secondary de Maistre move? First, for many kinds of coloring here on the endpoints, the number of states, the number of extensions is the same here and there, and contribution is 1 on both sides. So here we have just isomorphism. So nothing should happen. However, if, say, if the strings, one of them is boson, another fermion, then we have a variety of distribution of shunts. Here is a shunt, here is a shunt. It's straight. This is shunt, this is shunt. And if you calculate contribution from them, you will see that they just kill each other. And so this means that, it is right thing to do. They must kill each other, just because if you have this straight, this string straight, then bosonic part cannot be converted into fermionic. It should pass through some shunt. Okay? And those guys must just kill each other in appropriate way. Again, the signs here appear because of distribution of signs.
I understand. So this argument that state sum is unchanged, not
Yes.
homology.
No. But if I construct homology, then the differential should act in this way for the neighborhood of this event. And this is straightforward. It's simple. Everything is simple. What is happening in the third de Maistre move? First of all, there are many situations when you have no choice. If you start with boson fermion, then you will come to this. So after the move, you have to just to arrive to the same configuration as there, you should go this way. And there is one shunt on the way you have to make. So you have this and that states, and here this and that states. And again, of course, since the whole sum is invariant, the contributions from them should be equal. So no problem.
And can you give a similar description for Jones, or it is impossible to do this?
It is easy. And basically, this is this gives Havana homology.
With chance.
Which, well, there.
Because there you change the type of the crossing.
There, the states are just distribution of markers.
Yeah.
And well, wait. Not only distribution of markers, but choice of orientations on the strings.
Yeah, it was not directly related to chance there.
No chance. No, this is the difference between models. But it can be constructed exactly in the same way. So you just consider states for calculation of...
yeah, but you define states absolutely different.
Yeah, you must, because the R matrix is different.
But still, this feature that it had a single diagonal element was present for Jones also.
It is present, yes.
So you could try to play this just exactly the same.
I must even. I have to. No, but it is covered with other things. It is covered with marker. At this crossing, you can have this marker or that marker, and they are associated with different terms of sign. And in other points, in straight points, you have no choice for markers. Markers are defined by orientations and vice versa. And it was, for a long time for me, it was just a confusing point, because I thought that here it should be similar. Similar doesn't work. Now, there is a more interesting picture. Yes, so here we have a picture before the move. And surprisingly, it is much simpler than the picture after the move. So there are states which just have the same contribution before and after. And you see, they are somehow similar, you can guess. But we do not need to guess, it is just a standard situation. And after the move, we have much more states, but they again are paired, and in a very special way. They are paired positive and negative. This is the same chance, and here are the same chance. We have just different signs. Oh, wait a moment. No, who kills each other is these guys and that guys, of course. With one shunt kills with two shunts. So here, one shunt has two contributions, plus and minus, and it gives this and that. But they are paired with those. And again, there is no... yes, and these things, when you put their different signs, they will be those who will be presented before and after.
So after the move, you have 6 terms?
Yes, after the move we have 6, and before we had 2. So 2 of new are paired with 2 before, and 4 others just kill each other. And there is no choice. It's automatically done. Now, what is the differential? It was the most painful part. The most painful part is to find, to solve equation d squared equals 0.
You need to decide what are minuses, which way you shift minuses in the compass.
Which way I shift?
So minuses in the formulas. Minuses should correspond to some shifts. Or, well.
Minuses appear because we have shunt. Sometimes it appears even without that in a straight situation when you have just 2 fermions. But in all other situations, and also at maximum point, if I remember correctly. But in this situations that we considered here, they didn't appear. They would appear. I didn't present all the pictures. I checked all the pictures, but and they appear by rotation, and somewhere a sign jump out from the crossing to maximum. But you can rotate the thing. But then it would be distributed for all of them. That just the whole distribution of signs changes. Now, so we have states which are the selection of chance and signs. Let us concentrate first of all on selection of chance. So we need to define which are adjacent to which. Here, all necessary adjacencies already appeared. Let me switch here to the language of virtual diagrams, Gauss diagrams. So in the first Reidemeister move, the first Reidemeister move means that you have a new chord. No chord and new chord. And it may be a new shunt. We could have other chords here. Chords are oriented from top to bottom. They are equipped with signs. And the condition of alternating can be read from this Gauss diagram. So a part of our diagram made of crossings which are shunts changes like this. So we have original diagram, we add more diagram, and we assume that both of them are shunts.
So some lines are shunts, some chords are shunts, and some are not.
No. Let me draw only shunts. There are also some non-shunts. Forget about that. So in this situation, there should be differential between them.
So
somehow.
What you changed?
I just added new chord. So only one chord is added. Then there is two second Reidemeister move, which means that we add two new chords. Here the orientation didn't matter much. It did matter from the point of view of other chords. You know, this is under crossing, this is over crossing, then should be under crossing, and so on. So when you go around switching to chords as soon as you can, it should be all oriented each time when you switch, you go along orientation of the chord. And the orientation of the chord, let me repeat, is from up to down. Here, for the second Reidemeister move, the chords must be, they must be oriented in the same way. So that this is not possible to include both of them into a shunt. Either one or another one. But if one of them is included, then you can remove it and include another one. And it doesn't matter if chords here are crossing or not. This is another situation. And certainly the signs of these chords, which do not matter much, here should be opposite to each other, if the knot is not virtual. So in this situation, I have to take a shunt which involves one of these chords, and it should be adjacent to another state where this chord is replaced by the other one. And finally, for making the third Reidemeister move, I have a picture like that. this chord may be replaced with these two. Its original position was here, so, and they can be switched, and the endpoints can be switched. It doesn't matter. It's a local picture. They claim that nothing else is needed. But now I want to think about these pictures as just about pictures of the virtual knot corresponding to this state. Given a state with a picture like that, with Gauss diagram like that, I can remove this or I can add it. Now, contribution of each state is a monomial, non-zero monomial. It has a sign, plus or minus sign. Let us assume, and this is, I understand that this is a very unnatural thing, but let us assume that our differential acts always from plus to minus, just to prohibit that d square is not equal to 0. Because if you act from plus to minus, then you cannot get from this minus to plus. It's very interesting how to make grading, second grading. It should be checked if it is possible to make the second grading corresponding to the grading in knot floor Hegard knot floor homology.
So your differential is always from plus to minus?
Yes, let us assume that it acts from plus to minus. Then it is differential, at least.
You mean that never from minus to plus?
Never from minus to plus.
But when the homology is the kernel plus the factorial.
Yeah. And so what? It is categorification. It does not. I understand that this is a dirty trick. I do not like it.
But you need to check whether everything works, right? You need to check whether
But
the moves work.
then the Meister moves work, because the only thing which is happening there is this replacement of chords locally in the fragment that we see. The other chords do not change. And I understand that in this way we would have, say, even dimensional homology free, and torsion may appear only in the odd dimensional homology. Now you can make grading, second grading, just on the basis of the signs. Just counting how many negative signs are there and somehow normalizing so that it wouldn't change. But it's not really that important at this point. I just wanted to have invariant homology with two gradings, which categorify Alexander polynomial this, well, for tangles. And this is done. Now, the question, what are other gradings for which it is invariant? It's very interesting. And it's very interesting, of course, to find the relation to other categorifications of Alexander polynomial.
This was a crucial point. Can you tell what are chords?
So look, we have, say, a knot, and we consider its parametrization by circle. When you go along this chord, this knot, I go along parametrization, and at the crossing I connect the point on the parametrizing circle with its other, well, copy, what is placed to the same point. And we orient from up to down. And also we have to put here the sign of this crossing. And this gives what we called Gauss diagram, for these knots, not because Gauss had this. Gauss considered plane curves, immersed curves. And
almost true. When you look at Gauss' notebook, initially he's drawing actually knots. Then somehow he realized he will simplify. But first few pictures are actual knots.
But in the text, it is about immersed circles, and he encoded these circles not by picture, but by reading of. So if you put here letter, you put letter there and here, and there is no orientation then, no signs. Well, signs can be included, but here it is a very convenient language because really we should ignore everything which is not chance.
And once again, how do you prove invariance in this way?
How I prove invariance? Really, it was proven by those pictures on the pictures.
Yes, but in this, not in this picture. Yeah.
No. Look, for each Rademeister move, I have finitely many pictures of it, which differ from each other just by collection of orientations. And, what is fermion, what is boson, distribution of that. So for all of them, I can draw what is happening, and I can calculate the contribution of this part. The other parts do not differ. And the picture there is local. So other chords do not come. It is a local picture. So I forgot to tell you that when this differential is defined, then for each transformation like that, I have to check if this thing and that thing give you the same contribution. Because it depends also on other chords, which maybe get involved. But it will be, in the case of Rademeister move, they do not appear.
And so the differential just switches the sign of the shunt.
Yeah. No. Differential does the following. It either adds one new chord or removes it with this or that sign, or it switches from one chord to sort of parallel chord, so that in between there are no other endpoints of chords in this state corresponding to shunts. And the third option is two shunts are replaced with one, again with appropriate choice of signs. But this appropriate choice of signs is exactly one that makes contribution of them canceling out. So, well, the same, those who cancel out.
But you told about this rule that it takes plus to minus, so it's plus and minus, what, which plus is it?
Which rule? Remind me, which rule do you mean?
You said that your trick was that the differential acts from plus to minus and not vice versa.
Yeah.
And because of this, it
Right. This is correct statement. So each time when I have the piece which, so first of all, I have adjacency. I know that this state is adjacent to that. And their contribution differ by sign. And a priori, I do not know where to go, from here to there or from there to here. The only thing but up to now, I do not have any preferences. And now my preference is I want to get differential. So I even thought that, okay, we can define equivalence relation. But then equivalence relation would change Euler characteristic. If I just identify some states and consider equivalence classes of states which contribute the same, it doesn't work.
Do you have explicit examples of this Poincare polynomials
No.
Not yet.
No, it was done 2 days ago.
So we would love
With mistakes, and mistakes were fixed by evening yesterday. So sorry for that. It is very.
Now, you said yesterday that you were having trouble with the reverse two-move, and that got solved.
Yeah, it was another version of differential. I didn't realize that differential should be related with the definition of states. Now it is matching. So this is the change. I tried to use markers. So this was the last attempt to use similarity with Havanov homology, to use your markers. And in the previous checking of all this stuff, I missed one version of secondary de Maistre move. But now it is safe in the sense that no matter what I missed, I know that the state sum is invariant, and therefore the terms from individual states should cancel out under each of the Maistre move. So there is matching. And any matching defines the differential as soon as we keep in mind that these are adjacent states. I think that it may happen that similar construction works also for other link polynomials, or link homology, that it can be defined. I'm sure that it can be done and gives the same result as Havanov homology for SL2. For SLN, I didn't check. But for SLN, when you have not covered SLN, but in the fundamental representation, there is a notion of chance also. I didn't try to check if it works, but
not a single one. There should be different chance.
there is only one term on the diagonal of R matrix, basically, in these representations. But maybe I'm wrong somehow. Should be written down.
So we would love to see a paper about this construction in the archive at some point. We would love to see a paper in the archive about this construction.
Of course, I will do this as soon as possible. So I try to make a sort of presentation because it is impossible to draw all these pictures on the blackboard. I'm sorry that it changes the style of this workshop. Nobody did this before. Computer presentation. I'm very ashamed, but
Oh, there are beautiful pictures.
yes. And the pictures were ready long before that for some other occasions. So it's not that I could do in one day all these pictures. I could use. And somewhere the orientations are wrong.
Let's thank Oleg. More questions?
I would like to see a second de Maistre move once more.
Second de Maistre move, no problem. Come on. I think it was shut down automatically. Yeah. So here is the third de Maistre move, and one of many pictures. But
Can you show a second?
yeah. Oh, okay. Wait a moment. I have to close this thing and then. So look, we start with just.
So you have before and after. Before there is no crossing, that's okay. After, do you draw all possibilities, or it is just some?
Look, for this after part, there is no before part. Because here we have this fermion goes from left to right. If you have two parallel strings, there is no such option to jump.
Yes.
So all the stuff which appears after should cancel.
And should cancel homologically as well.
Yes.
Okay.
And it does. So you have this state and that state. Well, each of them stands for a huge collection of states. Any extension outside. But extension outside gives the same contribution. So I just calculated local contribution from these crossing points. And they have opposite signs, so they cancel out.
And both of them are coming from the same. There's differential which coming from something to this two, and they cancel. I don't understand.
No, the shunts here are different. This and that are different. And this and that are different.
But cancellations is possible only if they are neighbor adjacent to the same.
Yes,
state.
this is this setup or that setup.
Okay.
So what if we had lots of randomized one? What if we had lots of loops? Just take these two double intersecting lines and lots of loops in the middle.
No. This is local picture.
Totally local.
This is true. I want to accept all other pictures for this construction of differential, but I need only pure pictures where no other loops are present just to prove invariance with respect to Rademeister moves.
But you want your differential. But you want to have this different. You want your
Yeah, of
diagram
course.
to remember what differential. Let's say you have this diagram and add lots and lots of loops here.
Yeah.
Loops. Then these two lines were no longer adjacent in the.
Yes,
diagram.
but I have to check if the corresponding states give the same contribution. Let me do this. Because if they do not make the same contribution, I would lose this property that the differential preserves the Alexander filtration.
You mean you want to check if it's the same powers of U and V?
Yeah. Because this power may depend also. So look, say here we have this and that, which are canceling out. Imagine that we have a kink here,
Yeah.
and some contribution from it at the crossing, and kink there. Here it is fermionic, there it is bosonic. They can contribute differently. And I do not need to say that they are connected with differentials. I do not need this differential. I just want to play a clean game. I just define differential which preserves Alexander filtration, Alexander grading, and acts in this specific.
So here just pure canceling. There's no complication.
No complication.
I think we really would need to see the paper to understand this fully.
What?
It's a sophisticated construction, so we would really need to see the paper to understand this fully.
Okay. Of course, I must do this as soon as possible, so I will come back
And
tomorrow.
you're saying the third Rademeister move, really there were just cancellations, no complications inside.
So the only thing which may happen in the third Rademeister move, so third Rademeister move on the Gauss diagram looks like that. Well, the difference appears when you have these 2 points switched. It may happen, but let's forget about other pieces and look at just at neighborhoods of adjacent arcs. So it is not alternating. And what is above, what is below, there is a top branch, bottom branch, and mid branch. And the crossings are organized in this way. So to have alternating picture, we have to have this and that. It's okay. And separately this.
So you said you choose your being neighborhood adjacent, just that in the Meister move there is cancellation directly.
Yeah.
And it works.
It works. So it works just because it's not my fault that it works. It is because the state sum is invariant. I do not know why. I do not care about it. I thought that I must care, but then it would be very complicated.
Homology was not so simple. It was more complicated than the Meister move, I remember well.
Well, one should use this.
Well, it's fine to have a simple construction as long as everything works. I mean, it's welcome. It's welcome. It's easy to do computations.
No, but this approach wouldn't give a really different construction. It's possible to deform one to another if you consider just SL2 case. It's not a problem.
You didn't need the chain on the top.
Exactly, that's interesting.
What?
In the usual Coulomb homology, you seem to need to construct a chain homotopy to prove that it's invariant under the second Runner-Master.
No.
But maybe it isn't.
No,
It is
the
cone,
same.
it is simpler, but still it is not automatic. You have cancellation because it's cone with obvious cancellations, yeah, but still.
No, maybe. I have to think of it.
But here is simpler.
Yeah. But I have known the categorification of Havana homology in this way for many, many years, for more than 10 years. That's
16.
56. No. 16, no. Then I didn't try to do anything else. But about 10 years ago, I tried. And probably this would be done also then. But then I found this hyperfields in tropical geometry and left this completely.
That's one. Let's thank Oleg again.